Hi, how you all doing? Hope you're doing well. Well, this is my first in a series of videos about integration with hyperbolic functions. There might be some arc sine, arc cos and arc tan there somewhere as well, but mainly it's about hyperbolic functions. This is basically the final integration unit of A-level further maths, FP3, further pure maths, for those of you who are using that syllabus. Okay. However, if you're doing IB, these integral results obviously are important to you as well if you're doing the higher tier course. Okay. I'm just going to get cracking then, okay? But before I start with these simple examples, just to remind you that there should be a list of standard results in your textbook. So, for example, in my textbook that I'm using, here I've got a list of standard integral results, you see. It starts off with the basic integral of sine x is cosh x plus c, and it goes all the way down to the integral of arc sine, arc tan, arc cos, arc sine, arc cosh, arc tan, okay? You need to know all those, or as many as possible, or at least to know which ones are in your formula book so you can actually use them. Okay? Any that are not in your formula book, you've got to memorise. Right, let's get going. Okay, so the first couple are quite simple. Just to get us into it, yes, they are quite simple. So this one here, integral of cosh, 4x minus 1. Well, you know when you integrate cosh, you get sine. Okay, so your answer could be sine something, isn't it? And the bracket is a simple linear expression, so it's going to be sine 4x minus 1. And when we differentiate, using the chain rule of course, but in reverse with the integration, when we differentiate 4x minus 1, you get 4. So we divide by 4 because we're integrating, so we get a quarter. Sine 4x minus 1 and then plus c. Okay. At this level, that should have been pretty basic for you, so I'm not going to dwell on that. There are far harder ones coming up that I might spend longer on. Right, this one here, also pretty simple. Why is it pretty simple? Well, let's just remind us about differentiation, shall we? So in the differentiation units, you'd have had to differentiate y equals cosec. Crikey, how do I spell that again? I've not spelled that right, have I? Cosec x, yeah? And differentiating that, you would have got negative, I'll speak about that in a minute, cosec x, coth x. Just remember that when you differentiate the reciprocals of hyperbolic functions, you always get a negative answer. The reason is the reciprocals you can write as something to the power of negative 1. For example, that is sine x to the power of negative 1. And using the chain rule, you bring the negative 1 down. And so that will be the case when you're differentiating coth and sec as well. Okay, so just remember you get negatives for the reciprocals, and then it's cosec x, coth x. Okay, if you can't remember that, go back to the differentiation chapter. I'm not here to remind you about how to differentiate. Okay, but of course, then looking back to our integral, notice that you've got here the cosec coth. Okay, so first of all, our answer is going to be negative, isn't it? Okay, it's going to be negative, and it's something to do with cosec. So let's just leave a gap for the coefficient. Okay, so cosec, and it's 3x rather than just x, okay? Remember, it's not an angle. These trigonometric functions, they're angles, so I've not called it an angle, it's a value. It's about arc lengths and the hyperbola, isn't it, and all that. And then using the chain rule, differentiate 3x, you get 3, so that would be a third in front of that. And then don't forget the plus c. Okay, so negative a third, cosec x, so cosec 3x plus c. Do not forget, you can always check these answers by differentiating. Just one of the many reasons why I like integration, okay? It's relatively easy to check your answers just through differentiating again, okay? You can probably differentiate that in your head in order to get that, okay? Right, next examples coming up. Right, next couple of examples. I've put them both up at the same time just because I want to talk to you about the differences between them. They may look similar, but they've actually got completely different answers. Okay, this one, notice it's got a square root in the denominator. This one doesn't. Okay, so that's got a huge implication there, particularly when we look at the numerators. Okay, this is actually a standard A-level mathematics integral, so you should be able to do this in P3 or P4, for example. Okay, why is that? Because when you differentiate the denominator, you've got a multiple of that derivative on the numerator, implying that it's going to be I'm just waiting for you to think about it. See, a natural logarithm. You have to know that, okay? You have to know that. Remember, that is the general result, isn't it? That is, if I just write a generalization here, if you have a denominator, okay, call it f of x, if you perfectly get the derivative of that on the top, so it's f dash x over f of x, then your answer is going to be the natural log of f of x. Okay, just remember that rule, plus c. Put the modulus brackets in, of course, okay, because we generally do that with the integration stuff, substituting limits in and so on, making sure that the expression there gives a positive result. Okay, so you just need to know that. Okay, so that's just a reminder, just to look out for those. So even though we're looking at further maths integral stuff, the odd, well, actually no, not the odd, several simple integral results will be required here. Okay. So this one here is going to be a natural logarithm, and it's always going to be the natural log of the denominator, of course. And when you check by differentiate this, you get 2x, that's 4x there, so just put in another 2 at the beginning to make it correct, and then the plus c, of course. All right. So that's our answer to the first one. Right, the second one, okay. When you do differentiate the 1 plus x squared, of course you get a multiple of that on the top. You get a multiple of 2x on the top. However, this is rooted, which means if you differentiate all of root 1 plus x squared, you don't get the derivative of that being on the numerator. Okay? So it's going to be a different sort of answer. Here what we're going to look for is consider 5x multiplied by 1 plus x squared to the power of negative a half. Okay, consider it written in index form, and then just look for, well, obviously the answer has got to be something to do with 1 plus x squared to the power of something. So try the very first integral technique you learned of increasing the power by 1. Okay, and that will work for you. If you increase the power by 1, you get 1 plus x squared to the power of half, and then just check what happens when you differentiate that. So we differentiate that, you bring the half in front, and then you decrease the power by 1 to get the negative a half. Differentiate what's inside the brackets, you get 2x, and lo and behold, it's very similar to that, isn't it? You actually end up with x over root 1 plus x squared. I'm hoping you followed all of that. If you didn't, obviously just watch the whole thing again. But that too is a simpler P3, P4 integration technique. Okay. The only thing that's needed is the 5. So we'll write our answer as 5, and then either power of a half or square root. It's up to you. So I'm going to write it as power of a half. Okay, because there's nothing to be gained by writing it as the root, and then plus c. Okay. So I'm hoping those couple of examples are quite straightforward for you. All right. Next one. Right, we're still on the easy integrals, but what I'm just talking you through is some of the integral techniques that you need to be able to use to integrate these things. So already in the first few examples, you've had a reminder of some of the P3, P4 work that you just simply have to know, okay, to be able to do these things. Right, here's another integral. I've just missed off the dx, of course, just whop that in straight away. Obviously it's important because it tells us what we're integrating with respect to. But here I'm just going to show you another technique that's often used to make something much simpler. Right, so you might have spent a couple of minutes thinking about that already. Maybe just pause the video thinking, oh, I'm going to work this one out before he goes through this. But what you may not have considered is just splitting it up like this. That is, when you've got separate terms on the denominator there, you can just rewrite it as the integral of these two expressions instead. Let's just put all of that in brackets. Okay, dx. Okay, it's much simpler. This one here you might recognise. Okay, let me just show you again. Yeah, that was the last example I went through. Yeah, so we know that one already. We can just write down the answer. It's pretty simple, isn't it? So this one is going to be 5, 1 plus x squared to the power of a half. And I'll put a plus c on the end as well. So that was from the last one. So that's already quite straightforward, isn't it? Okay. And then this one, well, this is where you can use one of the standard integral results. That is that the integral of 1 over root x squared plus 1 is r shine x. Okay, you have to know that. Right? And so you've got 2 there, so that would be 2 r shine x. And then plus, let's just put the plus a bit more central, shall we? Plus 5 root 1 plus x squared plus c. Okay. In another video at some point I'm going to go through how you can work that out if you either don't have that list of standard results on you or don't actually remember the result about this integrating to get R shine, okay? Because there is a technique that you can actually use to derive that particular result through integration, okay? And I'll show you that in one of my videos coming up, okay? Well, that's all I've got time for in this video, all right? So maybe just have a go at some questions before you go through the next one, okay? Don't just storm through all my videos, okay, and think, oh yeah, I picked it up. You simply have to practice all of these, okay? You have to, once you've been shown a certain set of integration techniques, you have to practice them yourself until you are fully confident before going to the next section, okay? Well, I'm hoping you enjoyed this video, and well, stand by for the next one.